Hello and welcome to 10th lecture in 5th chapter of our comprehensive course on AI, ML and DS. In previous lecture we talked about measures of central tendency. We mainly talked about these parameters, that is the arithmetic mean, harmonic mean, geometric mean, three types of mean. However, most important is obviously the usual arithmetic mean, which we in common language called average, sum of two numbers divided by 2 or sum of n numbers divided by n if there are n observations. Then there is one another parameter called median. We also saw how to find median in case the number of observations are odd or number of observations are even. Then now we want to discuss this thing, measures of variation. They are also called measures of dispersion. Okay. Now the question, oh yes, we also, so this should have been slightly down actually. We also, because we had already discussed about this percentile, quartiles, all those things also. So, and box plot, interquartile range. Okay. We even saw this how to draw the box plot. So these measures of variation or dispersion should be here. Okay, fine. Little bit disruption because of misplaced cell. So sorry for that. Yeah, we did this quartiles, and we said that if this is the box plot, then this is the minimum value, this is the maximum value. The difference between them is called range. The first quartile is that observation such that 25% of the observations in the entire data set are below it and 75% are above it. Second quartile is that observation, this Y3, such that 50% are below it and 50% are above it. So that means this Y3 is actually the median only. Okay. And the third quartile is that observation, this Y4, such that 75% observations are less than it, below it, and 25% of the observations are above it. And the difference between first quartile and third quartile, that here the same box plot is shown horizontally. Okay, so the difference between first and third quartile, that is called interquartile range. Then this line joining the minimum value to the first quartile, that is here this line in this vertical graph, and here this line, that is called lower whisker. And similarly this line which is joining the maximum value with the third quartile, that is called upper whisker. Okay, so any point which is beyond the minimum or maximum value, they should be called outliers. Okay, now the question is how to define these outliers. Then most of the textbook and most of the standard method is that Q1, that is the first quartile, minus 1.5 times interquartile range, find that value. So this is Q1 minus something, so you are going somewhere here. It may not be minimum value, remember this answer Q1 minus 1.5 times this length, interquartile range length, that might be here somewhere here. Then any observation beyond that, less than that, for example these two dots are less than where my cursor is moving. Okay, so then that is called lower outlier. Similarly, third quartile plus 1.5 times interquartile range. So this is my third quartile plus 1.5 times this distance. Okay, this distance, that may somewhere be here. So if I have an observation here nearly almost at the right border of the diagram, then that observation would be considered outlier because it is at beyond this range, Q3 plus 1.5 times interquartile range. Now, why these outliers are important, that also you must understand. So we had also drawn one such diagram using NumPy and Matplotlib. And yes, one important thing is at that time I did not explain this code because this chapter is about NumPy. Previous chapter was NumPy basic and this chapter is NumPy advanced. We have not yet even introduced the visual or plotting library, but that's why we are not discussing this code. Any code on NumPy, I have explained every line of it, but this code at present there is no need to explain because it is in any case going to come in many other chapters. For example, you can see here 13th chapter, Introduction to Data Visualization, 14th chapter, Matplotlib, 15th chapter, Seaborn, 16th chapter, Advanced Seaborn, 17th chapter, Combining Plot and Interactive Visualization. So you can understand that we are going to discuss 5 whole chapters on data visualization. So that is why at present we are not discussing this code because I have written the code just to explain the point. So these are my observations. Okay, and how to find the mean value. At present you are just supposed to remember this much, that mean can be found by numpy.mean of my data, provided my data is first saved as a numpy array. And similarly by can be found is numpy.median data. Okay, harmonic mean cannot be found, geometric mean cannot be found by this NumPy library. For that you require SciPy library. So here if I execute this, it will give error because it needs the SciPy library. So let me see, perhaps in one other example I showed how to find that, and yes, here from SciPy.states. So you have to use the SciPy library, otherwise it will throw error. So here SciPy library is required, scientific Python. Now if you see, then these are various measures of central tendency. This is median, then it is somewhere 8 point something. Actually speaking, somewhere here 8.5. Mean is also 8.5. It's not necessary that for every data point mean and median are same, but here they are same. Harmonic mean is 4.7, and the geometric mean is 6.8, and the first quartile is this 4.75 point. So that means 25% of the observations are below it, and this second quartile is 8.5 point. So that means this point 8.5 median. So 50% of the observations are below it. Third quartile is 12.25. So this is that third quartile 12.25. 75% of the observations are below it. And then you are saying that it is the this is the situation. Fine. Now I want to show what is the effect of adding an outlier or a large value, and that shows why median is considered to be a very robust measure, but mean is not that robust, and also shows what is the importance of concept of outliers and why outliers are sometimes removed, but sometimes outliers are the important thing. Say instead of these, suppose these are my credit card transactions which I have done in past 16 months. With my bank, and suppose I have been associated with my bank for last 5 years, and in last 5 years also the transactions are in similar range, maybe jumbled here and there, but the minimum transaction which I do with my credit card is say $1, and the maximum transaction which I do is $16. So that means the bank's algorithm has created my profile that this fellow does not do big purchases on credit card, but rather he prefers to do transactions from 16 to $1 to $16 at the most. Now suppose someday instead of $16 a huge transaction comes like $16,000. Now let us see how it changes my graph and where that outlier point. This point is clearly an outlier point. So you can see that my graph has been squeezed almost. The box is not even visible. If I magnify a lot, then you will see something like a box. You can see something like a box. Okay, but it is not even visible to accommodate that outlier. Now the question is, for credit card fraud detection, if you are developing a machine learning solution, then will you remove this outlier? No, because that is the point in which you are interested, and your algorithm should detect it. But before feeding the data to the algorithm, you do data cleaning, and at the time of data cleaning, if you remove the outlier at that time only, then what will happen? That you can understand, your fraudulent transaction will never be detected. So here it is not required to remove the outlier. However, in certain cases we remove the outlier. For example, suppose some record of age of persons is there, okay, and the ages are written as say 25, 27, 38. I'm just randomly writing the numbers. 45, 66. Suppose in a hospital, the ages of patients are written in one column, okay, for 46, 30, 23, 67, and suddenly there is one observation, 230, and similarly thereafter again some observations which are normal, 23, 45, 41, and so on, and then there is suddenly another observation, say 108, 188. Now obviously, clearly, no human being ever has lived, according to the Guinness book also, more than 230 years or 188 years. So that means these are outliers, and here they must be removed. Before doing any further machine learning model building, you have to remove that. It is clear that data entry operator has done some mistake. Okay, so when outliers are removed and when they are not removed, that is one very, very important concept. Okay, here let me remove the number to 160, and let me show you that now at least the box plot is slightly visible, but still my data distribution is highly distorted by just one observation. If I see my mean, now mean is 17.5. So originally mean and median were same, if you remember, 8.5. Now mean has suddenly changed to 17.5. If I make that 1600, the mean will still change. It is now 107. That is why mean is considered to be a non-reliable measure of central tendency, because it is not robust to outliers. But median, you see that whether you write 1600 or whatever, but more or less median remains same. In this case, it remains exactly same. So that is why median is considered to be more robust. Let me make the data exactly as it was original, and because I want to keep the things as it is. So now my mean is again 8.5, 8.5, and I get a nice box plot without outliers. So now this discussion was required because outliers is an important concept, and there are techniques to remove the outliers, but more techniques are included built in Python. So there is no big deal about using those techniques, but more important thing is to know when to use those techniques and remove outliers, and when not to use those techniques and keep the outliers. So then that is the important discussion. Okay. And one another discussion also, another example also I can give. For example, suppose the cancer detection algorithm is there, in which lesion size in micrometer are given. In somebody's brain, there are lesions in micrometer 1 micrometer, 3 micrometer, 5 micrometer, 2 micrometer, 6 micrometer, 7 micrometer, 9 micrometer, but there is one lesion in one person's brain, 34 micrometer. Now, the uh, doctor, by his training, that is a neurologist or neurosurgeon, by his training knows that this much range of lesion in the brain is not worth operating. That means the risk of operation are far outweighs the harmful effect of the lesion. Suppose medical science says that up to 1 to 10 micrometer size lesion is fine, but this is huge lesion, and clearly that person may develop stroke, paralysis, or maybe some other kind of severe disability. So clearly this person needs to be operated. Now here is outlier. If suppose there is an X-ray viewing algorithm, and you will be surprised, but nowadays even radiologist work is done by machine learning. That branch is called CV, computer vision. Okay, so that computer vision algorithms are as accurate as, or sometimes even more than, a radiologist with 10 years of experience. So as a result, what is happening here, that you can see that if before feeding your lesion data to that algorithm, if you by mistake remove this observation, thinking that this is outlier, but here that is the point of that patient is the patient of who requires the real treatment. If you remove that patient's data thinking that operator has made some mistake, maybe it is less and something, no, you have to keep that. So when to keep outlier observation and when not to keep outlier observation, that is a very important discussion. So hence I decided to add this lecture before we now go to measures of variation or measures of dispersion in our next lecture. Thank you.